Hello everyone. Thanks for coming back to my channel promoting safety engineering. My name is Sean Toby. Thanks for watching the other videos I dropped about HAZOPs and the likes, and for the comments, and yeah, I'm looking at all of them and working on doing some videos to answer some of your questions. So thanks for coming back, and please do not forget to subscribe and like the video when you finish watching. Okay, so this channel, of course, you all know what I talk about most times. It's safety engineering, technical safety, process safety. I talk about HAZOPs, hazards, and the likes. So today, it's going to be a continuation of our former video, of the last video I did, which was I broke PNIDs into HAZOP nodes. I went through the steps showing the whole PNID, about maybe 15 pages, and then or 12 pages, and then using the PFDs I broke them down into nodes. And now this is a follow-up showing you the node 1, the HAZOP of the node 1. So gonna HAZOP the node 1 together, and I'll break down everything, what all the deviations are like, and how it applies to this HAZOP. So also, I love the fact that you asked a couple of questions were about how do we treat the other deviations, because I have a video on HAZOP also, well, which I did a HAZOP, and people ask, because I looked at flow, no flow, more flow, less flow, and stuff like that, but people started asking about other deviations like level, like temperature, the other parameters, and I was like, okay, I should do a video. So I would do a video on that and explain fully what all the other deviations, although we're going to treat some deviations on this node 1. So this is going to be a series. I broke this PNIDs down into 3 nodes. There's the green, which is node 1, there's the red or wine, which is node 2, and then there's the blue, which is node 3. So now I'm going to start from node 1, which is the green. So please subscribe to my channel and like the video once you find it enlightening. Okay, thank you very much. So now we go to the worksheet, and so this is gas plants condensation stabilization process. So of course, as I explained earlier, this is our HAZOP worksheet, and so before you go into your HAZOP, you have to know that you have to give all the parameters and fill up all the little things that are in the worksheet, like okay, so this appendix, gas plants condensate stabilization and storage project, this is a HAZOP worksheet. You have to name it node 1. Your node boundary, this is very important. So you go back to your node boundaries, explaining that where your node starts from and where it ends. So this is the beginning of the PNID. My node starts exactly here at this tying point, so which is what we've explained here, that CP004 to inlet of condensate storage day tank. So CP004, that's this. So that's where this node starts from, and it goes all the way to where the node ends. Can you see? This is condensate storage day tank. So this is the inlet of the condensate storage day tank. So the node, that's the node boundary. So the node starts from, so it's a description, starts from here all the way down there. So that's how you get your node boundary, which is here. Then of course you have to describe the system, because it's more reasonable to break your PNIDs down into systems. Then of course the dates, the number of the project, the HAZOP leader, that's yours truly, thank you. And then we go into the parameters. You want to give the parameters for the entire node. So you go into flow, which all this should be naturally on the PNID somewhere up here. If you can't find it on the first one, you go into the second one. It's always going to be here. You can see 90 meter cube per hour. You go back to the worksheet, you can see 90 meter cube per hour. That is the operating atmospheric operating temperature. That's operating pressure is atmospheric, temperature is 30 degrees centigrade, kind of almost ambient, just a bit over ambient, and then the composition is liquid hydrocarbon. So all those you can get from around from the everything from the top of the PNIDs. So you would have your pressures, you can see pressure, atmospheric, you can see the flow rates here, and temperature, of course, all those things are here. And then you use that, you pick them up from everything in the node, and then you use that to populate this. And then you go into the node intention. That's what the idea of the node is about, what you want to achieve with that node, what the node is supposed to do. So that, and what is it supposed to do? That's mainly, this is the condensate flowing from here, and it goes from this tank into the pumps, from the pumps into this tank, into this condensate storage tank, and from the tank it goes into another set of pumps, then into the condensate storage day tank. So to pump condensate from the existing surge vessel, which is here, this is the existing surge vessel, you pump out the condensates through these pumps, and then you pump them to storage tank, and further channel through condensate storage day tank to the truck loading bay. So applicable operations normal, then you give the numbers of the PNIDs. That's 000, 11, 12, 13. You get all those from here. So this is 11, you go into the second page. This is 12, going to the, then this is 13, like that. And you just write all the pages, all the PNID pages that you're going to be HAZOPing. You write everything down here. And then you go into the first parameter, and the most advisable parameter to start from in a lot of HAZOPs is flow. Because once that's part of the reasons why we don't talk too much, we don't go too much into, we go a lot into pressure and the other deviations like level. But once you treat flow really, really well, there's a good percentage of most of those, a good percentage that most of those things would show up under pressure, because when you don't have flow, you have more pressure on one upstream and you have less pressure downstream, and that also cascades to level, like no flow in the tank, meaning either the tank is going to be overfilling upstream, or downstream it's going to be you're not going to have any flow into downstream, so there's going to be less level. So it's either going to be more level upstream or less level downstream. So the flow also relates to all the other deviations in some ways, but not every single one, but we're going to treat them as we go along. So the first is, look at this. This is the first deviation, inadvertently closing this 6-inch manual valve upstream, the exit V 110001. So that's your first deviation. You write that here, inadvertent closure of 6-inch manual valve upstream XZV. That's a shutdown valve, XZV 110001. So look here. Yep. So this is that valve. So you have this valve inadvertently closed, and what are you gonna get? You're gonna get unable to evacuate condensate from V1100, which is this tank. This is this vessel, the surge vessel, V1100. So if this closes automatically, you cannot flow into this line. So this is gonna not have, so you're not gonna have any flow downstream. Upstream is going to be blocked. You're going to have more level here. You could have possibility of a liquid carryover into wherever equipment is upstream. That's not really what we're going to focus on now. But looking at this is closed, so no flow, and which automatically goes into unable to evacuate condensate from V1100, which is what's in that tank. Then potential for liquid buildup in V1100. Yep. So you can flow into this line, which is how you evacuate this such vessel. You can flow into it. That's, if you look down here, look, the flow comes this way, this way, this way into here. So you're gonna have potential for liquid buildup in the vessel, potential for liquid carry over to the flare. That means the flare is upstream this vessel. So this doesn't work. You have this doesn't flow. You have possibility of liquid level building up, then liquid carry over to the flare, which is upstream, and then you could have potential for a pump damage, P53028, which should be downstream, P53028. Yep. So if you look at the flow from here, it comes all the way from here and it goes into the second page this way and it splits into two. So these pumps could cavitate because if they're on and there's no flow into them, they keep spinning, they keep running, they get hot, and they cavitate. So you don't want that happening. So that's also another issue, that you could have potential for P5302. That's a pump damage and loss of production and revenue. So that means you won't be able to produce your condensates and you would be losing money. So those are the consequences. So yeah, sorry, I should have described this earlier on. The way the worksheet works, no, that's the guide word, then the parameter is flow, then the causes, consequences, your protection / safeguards, sorry about that, safeguards, and then you go to your recommendations, which is whatever way you're going to make it better. So of course the deviation is the guide, there's the guide word and the parameter. So it could, the guide word could be no more or less, then the parameter could be flow, it could be pressure, it could be temperature, it could be level. You have that. Then the causes, so what could cause a no flow? That's what we think of here. So we've said what causes a no flow is this valve being closed. It will cause no flow in our node. And after seeing that, then we look at, so what are the consequences of having no flow inside our node? And that is unable to evacuate condensate from tank, liquid buildup in this vessel, potential for liquid carryover in the surge vessel. And so those are the consequences. And then we go into the protection. So how are you going to safeguard against those things happening? So protection, SOP, that which means standard operating procedure. Let me standard operating procedure. This is very important, because this is things like your procedures, your guidelines, everything you do when you're operating the plants. Then also we have another safeguard, which is a trip, 1100 trip 003 high. So which means if you're not having any flow in this, there's a potential for this build up, for there to be a build up in here, and there's a high trip, which is this. So when this vessel sees a very high level of liquid, it would trip, and it would, that trip would probably cause a close of some upstream shutdown valve, so that we don't keep on filling this and have liquid going to the flare, because that could be very dangerous. And then so that's protection. Apart from a standard operating procedure, you have your level trip 003H, which is on your vessel. So obviously that would trigger someone in the control room, and probably also close close the vessel up, close the valve feeding the surge vessel. Then you also have the trip 530201 low, which is going to be further down. That's a low on the pumps. So if this pump see low, if they see low, that's, you can see this 5302. So if there is no flow, look at it coming from here. If there's no flow, there will be a lot of level in this, it will be very high. Then you go all the way down, then there would be no flow in the lines all the way to here. So this is kind of some protection for this pump cavitating. So that is this. If this sees very low level in this line, it automatically knows that this is not being fed and automatically would trip something. So you, of course, you have your cause and effects charts to see what each of these trips, but this is a protection to ensure that we do not have low, and if we have low, then something has to be turned off. So that's another protection to let you know when that valve is closed and to save you from these consequences happening. And then, so we can now say, okay, so how do we design it? How do we make it better? So this is a HAZOP PNID. So it's only the HAZOP, the use of the HAZOP is to make the system more robust, to make it better. And then, so we're looking at consider moving the PZA03 low to the suction side of the pump. Now that makes a lot of sense. So this is here, and it's downstream the pump. So meaning if this is low, this might have already been damaged. So what the recommendation is saying is, why don't we move this here? So this is the low before it gets to the pump, and we can do something about it before it damages the pump. So we can move this whole system and move it here and not have that happening. So that's a recommendation, although that would still be reviewed by the process team and they would decide. So those are the kind of recommendations you give in a HAZOP. Consider doing this, consider doing that, just to make the system better. And they, after you give the recommendations, the team goes back and deliberates and decides if they're going to use that the recommendation you've given them. And if not, they would close the action, but give a good reason why that doesn't make sense. Okay, so going further, so this is the next one. This is a manual valve. Manual valves can only be inadvertently closed. They do not fail in closed position. They do not get stuck because you actually have to open them yourself. And they're manual. That's why. So this is an XZV110. That's the shutdown valve downstream the surge vessel, and that's it here. So this is a shutdown valve. It's electronic or instrument air, and it's controlled. So this doesn't have anyone coming to open or close it. It works by itself. So as this is a shutdown valve, sorry, I'm pointing at the screen, I should be using the mouse. So this shutdown valve not working gets stuck in closed position. That could happen if it's not properly maintained. You could have a manual valve that just a shutdown valve that just sits closed, and then you have all these consequences happening again because it's just further down the line. And then so what you have is all this: unable to evacuate condensate, potential for liquid buildup, potential for liquid carryover, potential. You have all this happening, and then so that's why instead of just writing all this, we could write it down and we could just say same as in 1.1.1 above. That's this. And the same thing, the safeguards, those are the same safeguards that would pick it up when there's a problem. The trip on here, and that's the high trip, and the low trip further down the line. Also, there should also be a level high alarm somewhere here. There's also a gauge. All of this is local. You have to actually go to the vessel and look at this, but there are different things that should alert you when there's a problem there. Then going further down the line, so you said same as above, and then yeah, those are the safeguards. And then recommendations, well, no recommendations for that. But also we could say stuff like here we could also put in preventive maintenance, which is some sort of protection, because if you're doing your proper maintenance, you should your XDVs, your shutdown valve shouldn't get stuck closed. And also you could also say consider installing valve position markers. This is very good because when a valve, it shows the position of the valve in the control room. So if the valve is stuck closed, the control room will immediately see that this valve has a problem, or if it's stuck open, it would see that it's permanently stuck open. So you don't have to wait for all the trips and alarms, lows to go off, or the trips stripping off valves, closing valves upstream the such vessel. A position marker will just tell you in the control room that this valve is closed, and if you know this valve should be open, you immediately know there's a problem and go look at it. So that could also be a recommendation. Okay, then we go. So we're following the line. Started from here. We've looked at this. We've looked at this failing. So these are also manual valves. This 4-inch, this two 4-inch manual valves. If they fail, if they're inadvertently closed, you can. This is around the flow meter. You can have no flow. So inadvertent closure of any of the manual valves across FT110101, which is this, across this flow transmitter. That's the meaning of FT. It's a flow transmitter. So inadvertent closure of any of those manual valves, you still have same as above, same as above. So any of those valves getting inadvertently closed, you have the same problem of the liquid building up in the vessel, potential for liquid carryover, and you have this reading it that there's no flow here because these valves upstream have been closed. You have those. So after looking at those manual valves, inadvertent closure of manual valve at pump 5302 suction. So meaning so you go to, we're through with this page. There's nothing else that could cause no flow on this page, and we come here. Yeah, so this manual valve upstream the pump is what we're talking about. Let me go back to the, it's always good to really describe very well any of the 4-inch, because they're 4-inch manual valves across here. That's, it shows 4-inch here. The reducers from 6 to 4, reducer 6 to 4, then goes back to 6 and then comes in here. So this is a 6-inch and this is another 6-inch. The pumps are it should say somewhere here, those are things we could, recommendations that you should give us, the operating philosophy of the pumps. So you can say give operating philosophy of pumps 2 times 100. Can just put it there like a question mark. So is it going to be 2 times 100 or 2 times 50? So our boat running as well. Okay, it says here that there's a standby. Sorry, I didn't look down there, but that could also be a recommendation, so that when you're reading the PNID, you actually know that our boat running at the same time, or is one running and the other on standby. So that could be the operating philosophy. Like both could be running at the same time, so meaning both are 50-50%, or it might be one operating, one on standby. So we could have just this always running, and if this has a problem, this picks up. And you should also describe, is it hot standby, is it cold standby, meaning does it automatically, if this has a problem, does this automatically start working, or if it has a problem, someone has to actually go down to here and actually set it up to start working. Those are questions you could have in the HAZOP, and put recommendations on that. I could also say hot standby, cold standby. So this is mid-advanced closure of manual valve at P5302A suction. That's this. So this acts up and you don't have flow in here, which is gonna be the same things as same as above. Then you have your pump itself tripping. So say it's 2 by 100, so just one is operating, so this pump trips, it doesn't work, so we don't have any flow. It's not pushing condensate, it's not working. So what are the consequences? The consequences are same as above, and the safeguards are still same as above, but here you have a second pump standby. So if this fails, that's a safeguard. This would kick in. So that's some sort of protection. This would kick in and make sure that the plant is still running. So that's a safeguard. So that's why you have the two pumps. So here I said give operating philosophy, hot standby, cold standby, and the likes. So another issue that could happen, which happens sometimes during installation, is this is an NRV. It's called a non-return valve, or I could call it a check valve. Some people call it non-return valve slash check valve. This is just to explain it really well. So you have a non-return valve or a check valve in the wrong position. So that's saying if this were installed the wrong way, this happens a lot of time, especially during commissioning, pre-commissioning, commissioning, startup, when maybe the valve was removed for maintenance, or when you're just starting up the plant for the first time. And this has been because you wouldn't really know looking at the valve. So because these are valves that only allow direction in one way, you don't want flow going backwards into the pump because it could spin the pump backwards and cavitate it. So that's why we have this. And if this is not there for a centrifugal pump, you could also have that as a recommendation. So if it wasn't there, I could say consider installing a non-return valve downstream the pump. So it's there, but it could also be installed in the wrong way, meaning the flow cannot go in that direction because it's only supposed to go in the direction the non-return valve is facing. So assuming on the field this non-return valve is installed with this point here facing this way, so meaning this pump will be running against the dead end. It could cavitate it, or you may not be able to pressurize and start up. So that's also, so non-return valve or check valve in wrong position, and the consequences are you're unable to start up, or if it's after maintenance, you may have issues with the pump struggling to push against the closed flap of the non-return valve. And so you have to look at your startup and commissioning procedure. You walk the line. You could also have that walk the line, which means you run through the entire P&ID, following it on site, looking at the actual each of the valves, knowing that everything is as it should be. So you follow it all the way through, because in the drawing you're not going to see it being installed wrong. It's only when you're on site that you would see that this has actually been done wrongly. Then of course we have this manual valve here. So that's also another point of no flow. Inadvertent closure of manual valve immediately downstream of the NRV at the pump discharge. So you have unable to evacuate condensate from the surge vessel V1100, potential for liquid buildup in V1100, potential for liquid carryover, potential for pressure buildup at the pump discharge. So that's also another thing that could damage the pump. So if this is closed and the pump is just running against a closed valve, it could actually destroy the pump. You don't want that. So that could also, so I could also put in here potential. Okay, that's a protection. Potential for pressure build up at pump discharge leading to a potential pump damage. So that could also be another issue. And then what are you have your SOP, then you have your level trip high on the surge vessel, you have your pressure trip high. So now we've seen why this is here. This is a pressure trip high. So this just flowing against this would let you, this high would let you know that the pressure in here is just too much, and so something is wrong. The pump is pumping, but it's not, the fluid is not getting anywhere to go. So this pump here, this strip here would tell you that there's an issue. So you could have a high here, and then you could install a low here, so that I said why that this pressure transmitter could be installed here. So you could have a low here to let you know that there's a low level in here, or you could have a high here to let you know that this is just pumping against the closed valve. So that's some sort of protection. Then PSV 530201. That's the, it seems there's a, yeah, so there's a PSV here. So this could relieve the pressure into the flare lines if you're running against a blocked discharge or a closed valve. So you could have that happening here, that this would relieve the pressure to the flare. That's, and then also the line is fully rated. That's also a good one because you don't want a line rupture. So when you say the line is fully rated, meaning the line can withstand whatever this pump wants to dish out, so the line wouldn't rupture. Okay, so then from here we go into the next page. Okay, inadvertent closure of any manual valve across this PSV. It should be in a lock closed position, that for manual, yeah, potential for line rupture. So any of these valves, we believe that they should be lock closed, but we could have flow going in them. So this could lead to a line rupture. Normally, if these valves were locked, so you wouldn't have any flow in this. So looking at this, this leads to the flare line. Okay, sorry, it leads to the drain. It relieves to the drain. Sorry, not to the flare line. Yeah, because it's a liquid, so it only makes sense that it would go to the drains. So ensure the manual valves across this are locked open. So in case they are locked closed, meaning if you have high pressure on this line and if this is locked closed, you have the potential to actually rupture this line because the system to relieve it has been locked closed. This is closed. So you have this valve closed here and you wouldn't have flow into that system. It's very dangerous. So meaning you should always have it locked open so that PSV can actually do its work. PSV means pressure safety valve. So it relieves the pressure to the drains. So you want to have, that's a recommendation, to have it locked open. Or else if there's a line blockage, you could have a line rupture. Although it could be looked at as a double jeopardy, but it's also good to actually treat it. And you have inadvertent closure of manual valve at pump's common discharge header. So both pumps have a discharge header. So this is it. This is it. So this is a discharge header. This is a discharge header. So if this valve is closed, that could also be a problem because then it defeats the purpose of everything upstream here. So that valve closure of manual valve at pump's common discharge header, and of course we have same as above, which is here 1.1.7. So all those trips, alarms, the pressure safety valve, everything, the line fully rated, those are protections. Then also we go to inadvertent closure of any of the manual valves upstream this tank. So we've gone to the next page of the HAZOP. So this valve, and this valve, any of all these manual valves should close, inadvertently being closed. And what would we have? We would have the same as above. This is applicable at the later phase of the project when storage tank will be in use, because normally this shouldn't be in use. So you have the same thing. The tank, everything, you wouldn't have any flow. The plant could shut down, potential for liquid buildup, liquid carryover in the upstream equipment. Same, and also these are all the same protections. So from there, spectacle blind in the wrong position. That's looking at this spec blind. You have it in the wrong position. That's this downstream, this tank. If it's in the wrong position, if it's swung closed, Okay, this is upstream. Okay, in wrong position, unable to start up. You have to look at your startup and commissioning procedure. That's very important, because if that manual valve is in the wrong place, if it's swung in the wrong position, you won't be able to pressurize the line. Even when you walk the line, you should be able to see it. Then you have the PV530101 stuck in closed position upstream T5303. This T5303, that's where's that here? Okay, PV530101 stuck in closed position upstream T5301. Sorry about that. It's just getting a little bit ahead of myself. So is uh this is a PV. This is a PCV, a pressure control valve. It goes up, down, it breathes. So it kind of controls the flow into this tank. So what you could have this stuck closed or stuck open if it's not properly maintained. So stuck in closed position, that's because we're looking at no flow. If it was stuck in open position, we're looking at more flow. So same as above. So you have to make sure that you do your preventive maintenance, and then you have the trip in the surge vessel. You have your pressure trip downstream the pump. You have your PSV downstream the pump, and then your fully rated line. So you don't want that pressure control valve being in a stuck closed position. Then of course we have this manual valve here, another enclosure of manual valve on bracketing gas line for T5301. Okay, I think it's this. Yeah, so this is it. So you wouldn't have blanket gas. So unable to provide blanketing to T5301. That's this line here. If it's inadvertently closed. So you wouldn't have blanketing gas in this. And that could be very dangerous. And then potential for explosion because within the tank. So you have your pressure valve relief valve, sorry, pressure vacuum relief valve. You have it on there. That's this. So if you don't have it's a pressure vacuum relief valve. So if there's no pressure in here, instead of it to collapse, you could have this alleviating that, or and then also it could also be a pressure relief valve to relieve pressure to the flare. So you have that in here to protect you. Then PCV 0101 stuck in closed position on blanketing gas line. So that's this here. If it's stuck in closed position, just like this PCV stuck in closed position, you could have a problem there. So that same as above here, preventive maintenance, and you have the two PVRVs there for protection. Inadvertent closure of BV5301 blanketing gas line. Okay. Where's that BV? Okay, this. So you also have this BV5301 causing a no flow in the system. Come in here, pick it up. Same as above here, just the same thing here because it's all on the blanketing line. Then you have spectacle blind in wrong position downstream the tank. So you come downstream the tank and here. So this spectacle blind is in wrong position. You can't start up. You have all the same issues. This manual valve being closed also. Closure of manual valve PSB5301 potential. Okay. Oh. Of that manual valve. So if you have this manual valve downstream this tank T5301, if it's inadvertently closed, that means you can't have any flow downstream. Here, everything this level will just keep on building up, which could get dangerous also. So Level buildup in T5301, yes, we have that. Potential for liquid spillover to the drain, that's from the tank. So this is for overflow. You have liquid going into the drain, and so you have liquid building up in here. You have liquid condensate going to the drain. You don't want that. And then potential for P5301A damage, which is the pump, which should be the pump further downstream. P5301, yeah. So of course, just as I explained earlier on, this, you could cavitate this pump if it's not getting any flow. So from here, so if this is closed, the pumps downstream in the next page would not get any flow. So you want to make sure this is open during operations. So what are your protections after you have these consequences? LIA, that's the level indicator or slash alarm high, and then the level trip high. So go back here. Where was I? Lost. Okay. Yeah. So we have this 5303 high here to let you know that the level in this is getting too much. That's this one below, sorry. And then you have the alarm high. So, and a lot of times before you get to a trip, you should have an alarm. So this is getting overflow, is filling up above the normal operating level. So because this is closed, so you have your alarm telling you there's something wrong there. Then eventually you have your trip, and your trip is just going to close off. Maybe it's going to close this, or you would see that from your cause and effect chart, or close some SDV upstream. So these are the protections you have to let you know that you're not that this tank is getting too full. So consider moving PZA 5301 low to the suction side of PZA. That's the protection on the pumps downstream. So that's this here. Consider moving it here, so that if this, just like before, if this doesn't see any flow before it gets damaged, this here would have picked it up. So a low here would have told you that this is closed, and then you wouldn't have any pump cavitating. So you pick it up before it gets to the pump, and before it destroys the pump, before it's too late. So also, okay, so there was a tagging error somewhere. Yeah, correct tagging to, yeah, this. Okay. So obviously, for each of them, you're giving them to a team. ICNA is instrumentation and control. Process, of course, we all know process. So we give the actions to the team that's supposed to handle it. So inadvertent closure of manual valve across PSV 530101. PSV 530101. Where's that? PSV 5301. Oh, okay. That's here. PSV 530101. It's a potential for overpressurization of the tank. Yeah, so you could have that. So you make sure the valves are locked open, like we said before. So inadvertent closure of manual valve P5301A suction. So that's the second set of pumps after this tank. The second set of pumps. So you have any of these valves inadvertently closed, and so then you have same as above. You can flow level build up, potential for liquid spillover to the drain, potential for the pump damage, same. Then the pump strip, just same as this, because it's the same configuration we have above. If the pumps, this set of pumps to trip, it would also affect everything like in 117, and you have that tank, the C5301, the storage tank. You could have level build up, you could have liquid to the drain, because you can have a liquid carryover like in the surge vessel, because this is a tank, the excess liquid goes to the drain. And then You have that, the pump trips, the NRV in wrong position, just like before. Inadvertent closure of manual valve immediately downstream of the NRV, that's the non-return valve, at the pump discharge. Same thing that we had above. That's this two here. And then what's next? Inadvertent closure of any manual valves. Of course, the PSV, just like we had above. So this, any of the manual valves, this or this, because these two are exactly the same configuration. And remember, it's 2 times 100, A and B, so any of them could be running. So whatever happens to this could happen to this. So that's why we keep saying any of the manual valves. And that happens, and same as 1.2. Okay, so potential for higher discharge pressure level build up in this, potential for spillover. We have your trips, we have your PSV, and we have your SOP. And then so we also looked at the PSV in any of the manual valves across the PSV, which I just explained. Then wrong installation of the flow transmitter, unable to start up, because the flow transmitter only allows flow in one direction because it's actually calculating the flow. So if that's installed in the wrong direction, that's on the first page. I believe, yeah, it should be this. Can you see? That's why it has this direction, this arrow pointing this way on it. So if this is wrongly installed, that's facing the wrong direction on site, then you could have no flow and you wouldn't be able to start up because you wouldn't even be able to pressurize your lines. And then so that brings us to the end of no flow on this node. Unable to start up, commissioning and startup procedure. Now let me see how long I've gone. Wow, 46 minutes. I need to stop here. I'll continue the next one on less flow. So sorry. I thought I could finish up, but yeah, I would wrap it up in my next video. So I would start from less flow in the next video and go into the others and explain fully well. So once again, I thought I would be able to finish this. I'm really sorry. Once again, this is shown Toby, and this is Promoting Safety Engineering. Please like the video, please subscribe to the channel if you love what I'm doing, and let me hear some feedback from you. Remember, I also said I would give an explanation for all the deviations, less flow, more flow, as well as and pressure and temperature and level and phase composition. I would give an explanation for everything in subsequent videos. Thank you very much for watching. Do have a lovely day. Bye.